Hello and welcome. Today's session will be on the early age strength measurement of concrete. Before I begin, a few points of housekeeping. If you'd like to ask us a question, please do in the live chat, or you're welcome to briefly unmute and ask your question as we go through the details. I'll also try and stay online for a little bit of time after the main webinar today. Now, the topic is early age strength of concrete. At Papua Construction Testing Equipment, there are two particular devices which are very relevant to this. We have RPX Insight range of concrete temperature and maturity sensors, and we'll definitely be discussing the use of concrete maturity for early age strength in today's presentation. Also, Schmidt Hammers have a long history of being used for early age strength. So as we work our way through, we'll briefly discuss Schmidt Hammers, though in perhaps not as much detail as I would do in a dedicated presentation on Schmidt Hammers. There is, in fact, on our YouTube channel, a pre-existing presentation on this same topic. So if you'd like to learn a little bit more about the use of Schmidt Hammers for strength measurement in general, that's where to look for a few more details. So early age strength of concrete. I'm going to begin just a quick chance to define what I mean by early age strength and also what I mean by strength of concrete, because it's a little bit difficult to talk about measuring concrete strength before the normal time, before we understand what the normal time is and why it's done that way. I'm going to discuss a summary of methods, some of which PCTE supply, some of which are more general purpose, or what's currently being done using the existing laboratory facilities. So it's going to be a pretty broad overview. After I complete the discussion of the tools, their strengths and weaknesses, for those who'd like to stay a little bit longer, I'm going to also touch briefly upon some standards on concrete maturity and some of the mentions made in local state road authorities and other criteria which relate to the measurement of early age strength. So the early age strength I'm going to define as for the purpose of today's presentation, taking a compressive strength measurement of an in situ concrete element before the conventional 28-day compressive strength testing is done. And for compressive strength testing, this is an Australian presentation, so we're going to use Australian standards 1012.9, which defines the test procedure for concrete strength. We'll actually discuss a little bit about what that has to say as we go through. Now, the other thing to bear in mind is, of course, not only what early age strength is, but why you would measure early age strength, which raises the issues of what's it useful for. So practically, if you have a chance for concrete structures where the formwork needs to be removed, post-tensioning needs to be stressed, or if you're running a precast yard and something like lifting elements up is on a schedule, by knowing the strength of those elements when they reach their required strength for lifting or stripping or other actions, those can immediately occur, getting ahead of schedule, or essentially giving that security and safety of knowing things are ready to go, that you're not moving too quickly in cold weather, or if things are moving faster than expected, to get ahead of the game. And this is why early age strength is so commonly used as a tool for high-rise construction or precast yards. It lets them essentially improve upon their management of their schedules. So let's talk a little bit about the techniques we'll be discussing. There's two broad categories. There's categories based around still completing a conventional compressive strength test, breaking in Australia a cylinder sample and recording the strength at which it breaks. So we'll discuss early age cylinder test, which is sort of the default setting, and also co-location and match temperature curing. Now, the other option is, rather than breaking cylinder samples, it's instead possible to use non-destructive testing tools or temperature sensing tools to calculate the strength on the element as it exists without using compressive strengths for that measurement. And we'll explain how that works and how a correlated measurement is different to taking a direct cylinder strength break. So And I'll come back to this slide several times, but practically the biggest weakness of breaking cylinder samples is that they're gone. You can't break the same cylinder twice. So if you break and the cylinder's below the required early age strength, well, you either need to have a backup plan or need to act very conservatively. Whereas Schmidt Hammer testing and temperature sensor, maturity sensor based tests, they're going to be repeatable. If you take a Schmidt Hammer test for early age strength and you're not ready, you can come back again in a day's time and check again. You haven't destroyed anything. If you're monitoring temperature and time, like we do with maturity, that builds up consistently and it can let us know when that works. Now, I'll talk a little bit more about relationship quality and whether it takes into account in situ temperature as we go through the details. But first, I just want to talk a little bit about compressive strength tests so we're all on the same page about what I mean when I say concrete strength. So in Australia, the standard is 1012.8 for making a cast cylinder sample in a cylinder mold, and 1012.9 is breaking that sample and using that strength. Why do we have standards? Because if you don't have a standard, you don't actually have an agreement. So compressive strength is not a unique characteristic. It's not a material property. You can't define an exact, something like the conductivity of concrete or the weight of concrete. That's physical. We can measure that directly. Compressive strength testing has a lot of steps, and I'll go through each of those steps because a 28-day strength, which is the typically used sort of characteristic strength of concrete, is an agreement. It's a way to say, if we conduct the test at 28 days, preparing the sample in this way and breaking it this way, we can compare that to the next one and the next one and confirm the properties of the mix used to cast that cylinder are the same as previous and future breaks. Early age strength is a little different. We're not so much concerned with comparing that concrete's final strength. We're actually concerned with catching the strength at a moment in time. So there's different weaknesses, different strengths, and different considerations. I've also included in my slides a few more standards. The New Zealand standard for the same techniques. 1012.19 is an accelerated curing standard, which is relevant to consider if you're using techniques such as match temperature curing, which essentially a match temperature curing tank is very similar to an accelerated curing tank. We're still heating the water above standard laboratory temperature conditions. Also, 1012.14 defines how to secure and test a core sample. So a cylinder sample we cast in a cylinder mold. A core sample is drilled from and secured from the in situ concrete. So one way to get a sample that better represents the concrete on site is take that concrete away from site by cutting a sample out. So that's why I mentioned core samples here. It's also mentioned in some of the road authority standards about concrete pavements. So let's just quickly go through 1012.8, 1012.9. First, we have to define the casting of cylinders, the curing of the cylinder samples, their preparation for test, and their test. A cylinder sample is 1:2 diameter to length ratio. And the most common size is a 100mm diameter, but it's also a 150mm diameter. I do apologize for the doorbell. Now, the compaction of the concrete is defined as either rodded, using a metal rod of a particular geometry passed into the concrete cylinder a number of times, or external or internal vibration to remove air from that concrete sample. And that's quite precise, and it also defines which compaction can be used for which strength ranges. It also defines that covers must be used on the cylinder samples. And then they're cured. So they need to make it out of their molds into a curing tank or a curing environment between 18 and 36 hours of that cylinder mold being cast. Often the casting is done on site. They're transported to the lab between the 18 to 36 hour mark and placed inside. It also defines the temperature zones where 23 degrees or 27 degrees is the standard temperature for our curing environment. And also we have some further definitions like Queensland Transport and Main Roads require a wet storage of the cylinder samples. So in addition to the that's now accelerated curing. This is coming back to the additional standard. Provides additional requirements to cure at temperatures above the traditional lab environments. This is relevant for match temperature curing because it may be appropriate to take this into consideration when designing a match temperature curing procedure. Once we've got our cylinders and they've been in their curing environment for the appropriate length of time, then they need to be broken. To prepare them to break, they have to be cleaned up so that they've got a flat, flush surface, which could be the use of something like rubber capping, grinding to a flat surface, or the use of cement sulfur cap. So the cylinder is entirely parallel top and bottom. And then it's placed into the compression testing machine and broken with a load rate of 29 MPa per minute. So the whole reason that this is so carefully defined is if I ask a lab to do cylinder tests at 1012.8 and 1012.9, I know exactly what I'm getting for my procedures. And that's why I go to these procedures now, because once we start discussing compressive strength, we need to start considering what we mean by that. So early aid strength is still tied into this same procedure, but we either want to do the breaks at a time before 28 days, or we want to catch strength gain of cylinders which have been broken before final strength. We'll discuss under correlation how we do that. But let's just continue with direct methods first. So match temperature curing is the first attempt to bring the real concrete condition on site into our measurement of early aid strength. So if we only break a cylinder after 2 days, and it's been cured in lab conditions, we don't know if the concrete on site was sitting at 23 degrees. It very likely was not due to heat of hydration. So if we co-locate concrete cylinders in a steam curing environment for precast structures, if we core from the existing concrete or cast cylinders inside the concrete, they will be heated by the concrete on site, or it's appropriate if you've got water curing to locate the cylinders in the same water lines, or to use match temperature curing tanks. So match temperature curing tanks are intended to track the temperature on site and compare and match that to a wet curing environment. Now, the cylinders do need to go in as soon as possible, which is usually before that 18-hour mark when they're fully set. So consideration needs to be given to sealed molds, or allowing for them to be placed late, but acknowledging that that's not an ideal match temperature, or filling to below cylinder lids so they're not in direct contact with water inside that match curing tank. So the reason that we want to get our cylinder samples up to the temperature on site is if we increase the heat, we increase the speed of the reaction, strength is gained more quickly than the 23-degree curing tank. So that's a quick discussion of match temperature curing and breaking cylinders for early aid strength. Are there any questions or comments before I move on to discussing in situ correlations with non-destructive tools or with temperature sensors or maturity sensor systems? So again, you're quite welcome to unmute, or I'm also watching the chat for any questions. Okay, I will continue. Thank you very much. So when we start talking about correlation, how many samples? It's a good question. That's probably something to consider more with correlation areas, but I'm not quite sure exactly which context you're referring to. It may also be a question more for agreement between client and testing facility. So if you've got a second to clarify, that might help me answer. If not, it may be more appropriate to discuss that with the people planning. How many samples of compressive strength testing? So there is some requirements. It might be that you crush 3 cylinders at 28 days, or in addition to the LEH strengths. Is it safe? So it is safe to assume that the heat of hydration causes a sharper increase in concrete strength than a cylinder of the same concrete sample that is cured in a cooler curing tank. That's thanks, Nat Cox. That's essentially the case. But yeah, so there's some information in standard. There's also will be requirements according to the specifications you're working to or the projects you're working on for your cylinder brakes. Oh, someone's unmuted.
Yeah, I'd just like to share, it's Nat, thanks, mate. That I work in a precast yard, and according to the standards, we have to prove that it's reached at least 70% of its strength at 7 days of age before it gets delivered to the client. And you need your 28-day strengths as well. So we cast an extra 28-day strengths. You have 1 7 and 2 28s, and we have a third 28, and we also have release strengths. So we steam some of our units. So we have extra steaming cylinders that we put underneath the mold, so it's applied to steam the same as the concrete in the unit itself. And we have 3 of those, so we can crack one when we think it's going to be ready. But we've got a 2 spare ones, so we can keep steaming for another couple of hours if needed. So it all depends on your requirements, but as a minimum, 1 7 and 2 28-day cylinders.
Look, that's absolutely great context. Thank you so much. I really appreciate that. So let's, going forward with number of cylinders and braking cylinders for early age strength, let's look at catching strength without a cylinder break occurring for that particular cast element. We're still going to be using cylinders to back up our measurements, but they're used to create a correlation now rather than as the direct early age strength measurement. So 2 most common tools used is concrete maturity, according to the American standard, or Schmidt Hammer testing is quite commonly used as well. I've also mentioned penetrometer testing because it's quite common as an early set measurement for things like cement. Maybe it hasn't reached 3 or 4 MPAs, it's set solid. So it's worth mentioning as part of the discussion. Now, the first thing you'll see of our 3 correlated measurement, Schmidt Hammer penetrometer maturity measurement, is it's not a direct strength test. We're not breaking cylinders to catch our results. The other thing you'll see is that some take into account the in situ temperature, others do less so. Relationship qualities are very indicative, but particularly with a correlated measurement, the quality of your correlation is down to the data you have to create it. So let's start with Schmidt Hammer testing. Schmidt Hammer tests are an in situ test of the surface strength of concrete. So we use the Schmidt Hammer, we strike the surface a number of times, and it records a value that correlates to surface hardness. If we work in the concrete laboratory and we collect the surface hardness values from cylinder samples that are then broken, we can build compressive strength curves like the one on the right-hand side of the screen, which have a relationship between rebound value, in R, or for Silverschmidt models Q, and compressive strength. This relationship is tied to the samples that are broken. So ideally, if you're making a correlated measurement, you have curve for your winter mix, curve for your summer mix, curve for mixes for this project, curves for mixes for that project. Now, you will find with Schmidt Hammers in particular, they often have manufacturer information as well. The quality of the manufacturer curves are not as good for your project as curves you have built specifically, simply because the concrete they used isn't the concrete you're using. Now, Schmidt Hammer tests are taken on the surface. So if we're trying to capture what's happening internally, particularly critical strength gain around where the strength has to be, such as near along the path of co-extension tendons or towards the and other areas like that, a surface test may not be appropriate, and also may somewhat underrepresent the overall strength gain. But it is a very commonly used tool for evaluating in situ strength. And it can be used for early age strength, and it can be used for existing structures with slightly different care taken around the creation of the correlation curves. If you'd like to learn a little bit more about creation of these correlation curves, it is covered in my previous webinar on this topic, but practically you need a number of samples. You can see here a very large curve where they've taken more than 100 samples, and then they've created a matching relationship, and that converts between raw measurement and then compressive strength. Concrete penetrometer is a really simple tool. It's actually a geometric relationship on these devices. The surface of the needle is a 6.5 millimeter radius. It's pressed into the material, and it requires a certain amount of pressure to indent that material. So if it takes 3 MPa to cause a 50 millimeter indent, requires a 3 MPa pressure to provide a 6.5 millimeter penetration for that indent. That's the way these measure. They're used most commonly for setting and evaluation of very low strength, because low strength can be difficult with tools like Schmidt Hammers. And then finally, concrete maturity is correlation of a maturity index versus cylinder strength. So I'll just take a second to discuss what I mean by maturity index. If we measure the temperature of concrete, we're learning something about that concrete by doing so. I was checking the notes. So by catching temperature, we learn one point of information about that concrete. We learn an instant temperature. If we also record the time history, so temperature and time, we can learn how long our concrete element has been at a certain heat. So if it stayed at 40 degrees for 3 hours, we can mathematically consider how quickly the curing has advanced for concrete, which has been at 40 degrees for 4 hours. This is the basic principle of maturity. The maturity index, and there's a couple of options, capture the energy, how long, at what temperature, and we relate that strength gain to cylinder breaks. Now, the biggest warning of concrete maturity, something you must understand, is it is only an early age strength measurement. Schmidt hammers, breaking cylinders, all of these are a direct measurement. All of these catch a moment in time, but also are a definitive measurement of strength. You could do a Schmidt hammer test with the appropriate relationships for a structure that is 2 years old. You cannot use a temperature-based maturity measurement to catch 28-day strength. There is no information to use. You cannot go, oh, we didn't break that cylinder, let's go back to our maturity sensors to replace that test. It doesn't work that way. Maturity is used to replace early age strength breaks or other ways of catching early age strength. So that's the big warning. If you keep that in mind, you'll understand where it can help you and where it's not going to be appropriate. So the definition most commonly used is the American standard ASTM C1074. And there certainly are testing laboratories in Australia that are sort of worked with NATA to receive the ability to practice to that standard specifically. It's the standard practice for estimating concrete strength by the maturity method. I will go into a little more detail about this standard after we discuss this technique and how it's used. I don't want to go into the formulas until we've learned the basic procedure for setting up and using it. So this is an example of building a concrete maturity strength relationship. A minimum of 15 cylinder samples are prepared. So you see there's 15 prepared here, and they're breaking them across 5 moments in time, 1, 3, 7, 14 and 28 days. The American Standard defines that you cure C511, another American Standard. AS 1012.8 is similar, providing defined curing environments. And I do want to stress that is what the standard thinks. It's intuitive to think, oh, we could change that. We can try and adjust temperature gain. But the raw use of the ASTM standard is to maintain standard curing conditions. And also to record temperature at an interval of 30 minutes or less. So that means that you have a sufficiently granular gain of strength. Now, in addition to breaking these samples, we need to record the temperature that's occurring in the curing environment. So 2 additional cylinder samples are prepared with a temperature sensor inside them. So those are cured with the 15 break samples, and they catch the maturity gain of those samples. So this is where we get the bottom half of our graph, as shown down here. We can see that we have the increase in our maturity factor. In this case, it's temperature time, degrees C hours. And then we see that we have a relationship for gain of this maturity index to strength. So if we were going to use this relationship in anger, we can, for example, look at a 6,000 degrees centigrade hour result and see that that has a relationship to an MPa just below 25, maybe a 24 MPa strength gain at 6,000 degrees centigrade hours. This is what we use to build our relationship. And we can do this on site. So now if we take the same kind of temperature measurement device on site, we embed that into our structure, then we can watch the maturity gain and watch the matching strength gain, particularly for the Insight by RPX maturity sensors. Secured onto steel. These ones will automatically start. So this is a positioning for vertical horizontal placement. The temperature sensors with this orientation are kept off the steel. So we're catching concrete temperature, not steel temperature, because of the location of the sensors. And another critical point is, I've described one stage of building a maturity relationship. There's actually a datum or activation energy criteria we'll discuss when we look at the standards. So these are either being assumed or there's an additional laboratory stage to prepare the very best strength relationship for concrete maturity. The final thing I want to point out on the use of this kind of technique is it assumes the mix has not changed. And if the mix does change due to change in materials or some other factor that's not noticed, the maturity relationship will drift. The relationship won't be as good, or it may no longer be appropriate to use that relationship on site. So there needs to be a confirmation stage, which could be done as simply as doing some conventional early age cylinder breaks and matching those up again with a temperature sensor of a cylinder traveling with those early age cylinder breaks. So if you don't have confirmation on your maturity procedures, you don't know if that relationship is still valid 2 weeks, 2 months, 2 years after it was developed. So do keep that in mind as well. Maturity is particularly dependent upon capturing the effect of your concrete mixes. So relationship built for one mix is not appropriate to use for another mix. And you need to confirm that your mix is staying the same. So I just change over so I can see any comments in the chat. So nothing coming through there. So now just a quick moment for questions before we go on to talking a bit about the nitty-gritty, looking at some of the formulas and how these maturity relationships are developed.
I have a quick question, William. Mm-hmm. If you have a graph with a linear line like you have, if you have another unit with the same mix, same conditions, but it increases in temperature slower over a different period of time, can you still use the same correlation formula to calculate. You know what I mean?
So, okay, so let's give me 1 second. I'll come back to my graphs. Sorry, I'm working just a little tricky with the way I'm got my monitor set up. So, okay, so I've got this graph here. This graph with the straight line, that's actually the maturity relationship. So that's developed from the breaks and the standard 23-degree curing environment. Do I understand that your question is about putting a temperature sensor in your actual element you're casting? Is that correct?
Yeah. So let's assume that we've cracked a shitload of cylinders and we've measured it all with in situ temperature sensing equipment, like you had on your next picture, and we have a correlation for one sample.
Okay, so one thing I would point out there is you wouldn't necessarily do that relationship with in situ sensors. So if you look down at my little diagram just here, you see I've got the 2 green cylinders. Those are instrumented cylinders. They go in with the cylinders being broken.
Yeah. Yep.
So
okay. So let's assume that that's happened then, and then you get a graph.
Yes.
So and then we get a formula that we can apply to the next time to say, okay, it's safe to assume that it's going to be 20 MPa based off this formula using this time and this degree hours. So same mix and everything. If we have a different line, but we don't do another line, sorry, if we have another unit, but it's much lower temperature over a different time, can we still apply the same correlation formula to assume the MPa from or maturity of that one as well?
That's absolutely the intent. The intent is you create under very controlled conditions your relationship formula, maturity factor to strength gain. Then you use that by putting temperature sensors on your in situ concrete to catch if its strength gain is fast or slow. So if you've got a cold cast for some reason and it stays at a temperature, let's say it was at 15 degrees for some reason over the time of its curing, rather than the 23 degree that your samples were, the gain of maturity index, because they all calculate on time and temperature, will be slower. So if you look at the MPa at your 5-day mark on your 5-day, so let's say the 7-day mark on your 7-day crushers, that'll have a high maturity index, and your lower in situ concrete will have a lower maturity index on the same day. So it'll catch that it hasn't gained as much strength. That's the purpose of this exercise.
Okay, gotcha.
Does that clarify?
Yeah, yep.
Yeah.
And I also have another question. I might be jumping ahead a little bit here, but do these need to be recalibrated, for lack of a better word, every 6 months?
Yeah, this is exactly what I'm talking about on your confirmation. So the relationship is built for that mix. And if that mix stays absolutely the same, the relationship is still valid. The gap comes is, do we trust that's going to be true? Or do we take steps to ensure that it remains true? So confirmation is the step to make sure that the work we did 6 months or 12 months ago is still valid today. And that doesn't necessarily need to be a whole new curve build. It can be confirmation cast. So maybe you put 5 cylinders in and a temperature instrumented cylinder like we did during our initial cast, and you break those. And you make sure that when you break them, the strength that they come out at matches close to the maturity index estimated strength that you're expecting them to break out. Does that make sense?
Yeah, no, of course, it's the same as a lot of other calibration curves. Yeah. You do a recheck at 2 of the main points that you're basing it on. That you use
exactly right.
So my next question would be: this is fairly early in my field of trying to get this across the line to be accepted within our industry. But in any industries, is there an acceptable time frame for that? Is it 6 months? Is it 12 months that you need to check it? Is it every month?
I'm a bit less familiar what's going into particular contracts, so I can't speak exactly there, I'm afraid. The standard does actually have some criteria in itself. If you go through the details, it discusses about doing it.
Is that ASTM?
Yeah, that's the ASTM
1074?
Standard.
Yeah. All right, I'll have to study that up. Thanks, mate.
Yeah. Let's keep going. Sorry, again, I just need to bring up the screens again. And let's just go to this is the bit where you're quite welcome to finish up now if you just wanted to learn how to use these tools. This is more about talking about ASTM C1074. So American standards are quite interesting. They tend to be very specifically good at defining exactly what a test method is and its procedure and documentation. They are not so good at defining interpretation of data. So whenever you read an American standard, know that what's most likely going to be missing is guidance on interpretation and use. But a very good definition of what the technique is. So if someone says concrete maturity and they refer to ASTM C1074, it's a very precise definition. The standard defines two mathematical functions, which will give us our maturity index. It also defines the procedure to develop the strength maturity relationship. And that's a specific procedure. Sometimes people will work to different procedures, so they're going beyond the standard. They define the instrumentation to be used on site. And as Nat's mentioned, they actually have some information about confirming that the correlation built in the lab remains true. A couple of very big limits that it makes very clear in the standard is this technique assumes that concrete is maintained in a condition that permits hydration. What do I mean when I say that? I mean that the concrete needs to have the chemical reactions continuing. If it gets too cold, or if there is insufficient, sorry, not too cold, if there is insufficient water to allow that chemical process to occur at its natural pace, you will overestimate strength gain. So if your concrete is not properly cured, your maturity relationship will not follow. Now, it doesn't take into account long-term strength or 28-day strength, as I mentioned. So it must be supplemented with something like a 28-day cylinder break for your characteristic strength, for your quality control strength. The other factor is, of course, the quality of the strength estimated on site depends upon a good relationship set up well. So that's all down to time in the lab and the procedures followed. So the first maturity index is the temperature time factor, also known as Nurse-Saul. It is looking at the area under the graph. There's a additional, so the factors that go in is the time interval, average concrete temperature, and a datum temperature. And the data temperature is where the mathematical model considers strength increase stops. This is when the concrete is so cold, it's no longer gaining strength. And that datum temperature, there's a procedure to establish that in the lab. If that procedure is not taken, then that datum temperature is going to be an assumption, and that needs to be considered as one of the assumptions you make in using this temperature time factor. It's very common for people to build maturity curves, but to assume the datum temperature. So that part does not necessarily match up with your mix. So just be aware that's an additional factor. The other maturity index used is called the equivalent age. It assumes that strength development obeys the Arrenhius equation. It's a formal equation used in other areas of activation energy, of chemical reaction. And now, rather than datum temperature, it has an activation energy. So again, same thing. The point below which we consider strength gain does not occur. And again, this activation energy is an additional input to that model that is sometimes determined experimentally and sometimes assumed. And if you're making that assumption, understand it is an assumption. So that's these two relationships. When we use maturity, this is what we're doing. We're using an equation that models concrete strength gain, and our curves and our relationships are based upon this mathematical model. So when we're doing things like confirmation breaks, we're confirming that our mathematical model matches the real performance, the real chemical performance of that material. And there's two assumptions that go into that. It's the datum temperature for Nurse-Saul and the activation for Arrenhius. And again, your ASTM standard defines the calculation, the formulas, the additional laboratory procedures to establish those fixed criteria, and the confirmation. A couple of local notes. Specification 8020, which I believe just is a Queensland specification. Sorry, unfortunately neglected to put my states on this, and I normally can see my notes, but I can't today because I'm working from home.
WA.
Sorry, thank you. I appreciate that. Is one local approach to catch strength, and this is talking about placing cylinders within steam covers. R82, which I believe is a New South Wales one, I may be wrong, is a description for when laying concrete road materials, in order to catch the early age strength and the cured strength of these materials, this is where they're actually securing core samples, drilling samples from that, and breaking them. But they've also defined a few modifications to our 1012.14, which is our standard for taking cores and breaking them. It's adding a criteria for a wet conditioning and some dimensional criteria as well. So even if you've got a local criteria which references an Australian standard, it may have additional criteria or may relax criteria depending upon its particular intent. I believe 610.16 is a Victorian document, and it does mention maturity as an appropriate tool, defining as appropriate for early formwork removal, precast lifting and loading. And this one puts the onus on the people using these tools to have a documented methodology and their own evidence of its performance. So this is again where that confirmation comes in. And it also separately defines using again co-locating cylinders with steam or radiant heat curing to again try and get that match temperature going on. So coming back to our criteria, to our techniques, again, the direct measurements of the normal early age cylinder test where we cure them at lab conditions and break them early, the co-location of cylinders in the curing environment, or the creation of a specialized curing environment that matches the temperature on site, have the advantage of we're still doing our compressive strength test. Match temperature curing also has the advantage of catching in situ temperature, and the co-location techniques certainly endeavor to do so as well. The advantage of catching in situ temperature is if it's hotter on site, strength gain will occur more quickly. So by measuring, using a early age strength technique that captures in situ temperature, we can actually attempt to improve, and we can actually attempt to better model strength on site with either our early age breaks or using a correlated relationship. The relationship qualities will depend upon care taken. And also there's going to be equipment requirements and there's going to be setup requirements in the lab, particularly our two correlated methods where we're building Schmidt Hammer relationships or maturity relationships. They let you remove your strength breaks to some degree. It's never going to be 100% no early age strength cylinders, but it's going to supplement or reduce that requirement. But the other side of that bargain, of course, is you've got to spend the time building the relationship so it can then be used to improve the procedures. And that's true of any correlated measurement. The better the input, the better the quality of the relationship, the more useful it is. And the better it'll pass confirmation. So that's really the main topics I wanted to cover today. So I'm very happy to take some questions before I finish up, but thank you for joining us. I'll probably finish my recording now, and then I'll go into some questions. Thank you.